So let me start the recording first. This is the chapter we started last week, but we didn't finish it. We almost finished, but not yet. So let me move to the slide that we didn't finish. Yeah. Okay, this was the example problem that we started last week, but did not finish. In this example, a frictionless flow is taking place in a pipe reducer shown, and because of the reduction, because of the Bernoulli's equation, you know that if the velocity increases, then pressure must drop. Velocity increase because A2 is less than A1. It's a reduction in the diameter, which means velocity must be greater than V1. And due to the Bernoulli's law, it requires that P2 must be less than P1. So this reduction in the pressure can be seen here. You can see that there is an increase in the pressure in the left-hand side, and this is because of this acceleration in the flow, which results in a pressure reduction. Here, it also says that the H, which is the pressure head, is proportional to the square of the flow rate. H, remember that P is gamma times H, and this H is called the pressure head, and it's proportional to the square of the flow rate, and which we will show it. So it's frictionless, so that we can write the Bernoulli's equation as the sum of the static pressure plus dynamic pressure plus the potential energy. So this is the pressure that we normally measure with the manometer. This is the pressure due to the flow velocity, and this is the velocity due to the height of the fluid column. So this summation is called the total pressure, is constant according to the Bernoulli's law. So it means if it's constant, the left-hand side should be equal to right-hand side. First, we can start with the conservation of mass. Conservation of mass means that mass does not change. Mass flow rate does not change. Here, rho is the density, v is the velocity, a is the cross section, and it's constant according to the conservation of mass. So from here, you can obtain the velocity v1 in terms of v2. As you can see, velocity is inversely proportional to the cross section. If the cross section decreases, velocity must increase in order to satisfy the conservation of energy. And now this can be written as m dot is equal to rho times VA. This part is called volumetric flow rate, sometimes Q dot, sometimes Q, but in any case, the VA part is called volumetric flow rate, and it has the units of cubical meter per second, whereas this one has the units of kilograms per second. So when we write the Q as A1 V1, which is equal to A2 V2, because rho is constant. Normally, if it's air, compressible substance, then we cannot write it, but because it's a liquid flow where the density is constant, we can write as the equation of equality of volumetric flow rates. So we put everything in the equation, Bernoulli's equation, and write the pressure difference P1 minus P2 as a function of V2 only, because we have written V1 in terms of V2, and V1 and V2 are correlated to each other as the inverse relationship of the areas, cross-sectional areas. Besides, we can also write the pressure difference between this point and this point. Remember that in manometers, when you go up, you take the sign to be minus. When you go down, you take the sign to be plus. So here, you go up as the pink fluid, which has the height of total height of L plus H. Then you have an equal side here which cancels each other. Then you go down with this gray fluid with a plus sign, and you go down with the pink fluid with a minus sign again. So it seems that actually this part cancels that part. So what you are left with is the density pressure difference as P1 minus P2 being equal to you go up minus H times gamma 1, and you go down plus H times gamma 2. Gamma 1 is the pink one, gamma 2 is the gray one. So when you combine everything in the pressure equation, you see that you have P1 on the left-hand side, P2 on the right-hand side. This cancels that. So all you are left with is this. So this one belongs to the pink fluid, and this one belongs to the gray fluid. So it means that the pressure difference between 1 and 2 is 1 minus Sg. Sg, remember that, rho of the fluid divided by raw water. And most of the time we take the raw water to be 1 kilograms per cubical meter. So this is called specific gravity. So 1 minus specific gravity times gamma H is the pressure difference between the points P1 and P2. So you just enter this value into this equation, then you get the pressure head H in terms of Q, the ratios of the areas, as well as Sg. So the ratios of the areas as well as Sg. So everything is constant here except Q, which means H is a function of Q squared, as was indicated in here. This is just a parabola, as you can see. So the variation of pressure in a flow is parabolic function of the Q. So you can write it, you can see it in many places. H, or pressure, always change with Q or V as a second order polynomial, which is a parabola. Up to now, we mentioned that in the Bernoulli equation, we assume there is no friction, there is no loss, there are no power adding devices like pumps or power extracting devices like turbines, but in real life, there may be inclusion of pumps and turbines. A pump increases the energy overflow, so pump adds energy to the flow, whereas turbine extracts energy from the flow. So when there is a pump, you use a plus sign in the energy equation. When it's a turbine, you use a minus sign in the energy equation. So with the addition of pump or turbine, and also if you assume that there are losses due to friction, the original Bernoulli equation has some additions. So on the left-hand side, you have the 0.1, but on the right-hand side, you have the right-hand side plus the additions of subtractions from the pump and turbine plus frictional losses. Actually, this work due to the pump and turbine is W turbine minus W pump, but because it's on the right-hand side, when you move them to the left-hand side, you get pump to be plus, turbine to be minus. Then HL is the losses due to the friction. So if you write everything in terms of friction, and if you collect everything on the left-hand side, you have pump term, which comes into play as plus, turbine term, which is minus, and loss term, which is also minus, which means pump adds energy into the fluid flow, turbine extracts energy from the fluid flow, and loss definitely removes energy from the fluid flow. Remember that in the calculation of pump power in vapor cycles, steam cycles, we said that the pump work or pump power is calculated from V dot times delta P. V dot here is the volumetric flow rate. So you can see the same thing here actually. So V dot divided by gamma Q is H, because as you remember, P is gamma H. So the turbine head can be written as turbine power divided by gamma Q, and pump head can be written as pump power divided by gamma Q. And because they are on the left-hand side, they should all be greater than 0. Otherwise, you cannot write it as it's written here. If you collect everything on the left-hand side, the pump power, pump head, the loss head, and the turbine head must all be positive. Of course, they have their signs in the front. So mathematically, they should be all positive figures. But of course, in the calculation, you use a plus sign with pump, minus sign for loss, and minus sign for turbine. An application of this energy equation. Why do we call it energy equation instead of Bernoulli's equation? Because in Bernoulli's equation, we assume that there is no friction, and there is no pump, there is no turbine. The difference between the energy equation and Bernoulli equation is the inclusion of losses plus pumps plus turbines. When you remove them, it becomes a Bernoulli's equation. So here, there is a flow in this pipe. We don't know whether it's upward, or downward. We don't know this. We need to find this out. The location, the pressure at the location 1 is P is gamma times 3. This is P1. And the pressure at location 2 is gamma times 0.5. We know the pressures. We know the elevation difference. So when we write the energy equation, we have P1, P2, the elevation difference between 1 and 2. So let's write the energy equation between 1 and 2. So without this, it becomes Bernoulli. But it's not Bernoulli equation now, it's energy equation. The left-hand side has the pressure head, the dynamic head, the elevation head. On the right-hand side, pressure, dynamic head, elevation head, plus pump head, loss head, and turbine head. But because pump head and turbine heads are zero, they're not given. When you cancel them, you get only loss term on the left-hand side. And because, as you can see, the diameter does not change. If the diameter does not change, V1 is equal to V2 because there is no change in the cross section, which means that cancels also the pressure term, the dynamic term. So from here, when you obtain the loss head, you will find that it's positive. What does it mean to have the loss head to be positive? We indicated that in this equation, all the terms must be positive, except they have their own signs in the front, but mathematically they must have positive. So now that the loss term is positive, by the way, we have assumed in the beginning of the problem that it's upward, then the flow is upward. If this had turned out to be minus, you would say the assumption that the flow is going upward is not correct. Flow must be going downward. Another example is regarding extraction power from the fluid power. This is a hydroelectric dam, let's say. There is a elevation of 100 meters of water. At the bottom of the dam, there is a turbine. So you will write the energy equation with elevation terms, pumps terms, and loss terms and everything. So at the end, when you write the equation, you're going to obtain, for instance, turbine power, also mass flow rate, velocity of the flow, etc. So first thing to do is to write the energy equation. The energy equation has only it's arranged to have the turbine turn alone, so that there is no pump here. Pump term is 0, but pump here, pump term is 0, but we assume that there is loss term. All the rest comes from the rest of the equation. This is the left-hand side, this is the right-hand side. So we have just arranged the energy equation so that we can obtain the turbine head as a function of the others. So when you use the given values, for instance, the elevation head is 100 meters, the flow velocity is not given, but you can, no, it's given, sorry. Velocity is given. So by using the flow velocity, you use it here. Then there is something you don't know yet, but the turbine head is 98 meters minus HL. What does it mean? It means that if the loss is 0, there is no loss, then turbine head will be directly 98, but this uses some of the available turbine power. If you assume that losses are 0, then the turbine head is 98. You just put the numbers in. Gamma is 9,800. Q is A times V. And the head is 98.2 meters. Then you get the power of the turbine to be 4.5 times 10 to the 3 kilowatts or 4.5 megawatts. What kind of losses can exist here? So we assume that the losses were 0. But in reality, there are losses. What kind of losses can there be? Losses in the pipes, right? Pipe losses, friction losses. And we have assumed that the turbine has 100 power efficiency, but most of the time it's not. So it may have something like 80% efficiency, meaning that 20% loss there. So turbine losses, etc. So if you include all this, you're going to get an overall efficiency of maybe 80% or 75%. So it would use up some of the available power from this 4.5 megawatts. So instead of 4.5 megawatts, electrically or mechanically, it will produce, let's say, 3.8 megawatts, and 3.8 megawatts is the mechanical output of the turbine, but it's going to rotate a generator, and that generator might have some efficiency, like 95%. Generators have high efficiencies. At the end, your available power would be something like 3.5 megawatts. Here you have pump this time instead of a turbine. So fluid here at this location is being pumped up here by using this pump. So the difference between this one and the previous one, instead of turbine, you have pump this side this time. So you will write the energy equation again. I have converted everything to SI. So you can see that this is the SI conversion of this. And it says it's 10 horsepower. It's the power of the pump. It's the power of the pump. So 10 horsepower is 7,460 watts. And also the flow rate is given as 0.05663 cubical meter per second. So we always start with the energy equation, but this time it has pump term instead of turbine term. Pump term is positive on the left-hand side, but it becomes negative on the left-hand side, but becomes positive on the right-hand side, and when it's on the right-hand side, it's negative. So here we leave the loss term alone. All the rest are the same, except there is an inclusion of the pump term. And pump head is similar to the turbine head. It's W, pump power divided by gamma Q. So we get a pump head of 44 feet, which is 13.43 meters. So if you put everything in the equation, there is something interesting here. This is open to atmosphere, so P2 is 0. This is open to atmosphere, so P1 is 0, or they just cancel each other. And because the surfaces are so big that velocity also is 0. So on the surface of the section 1 and on the surface of the section 2, velocities are 0. So if you put these values here, the pressure terms is 0, the velocity terms are 0, and if you assume that the reference is this one, here is the reference height, so this is reference height, so it means that at this location Z is 144 meters, so you just assume that at the lower section the Z is 0, at the higher section Z is 39.1 meters. So if you calculate the loss, you get 14.1 foot or 4.29 meters of water. It means that you have to overcome this loss so that the water can be pumped up. So the first thing is to overcome this. What is the equivalent, power equivalent of this loss? You can just calculate the power loss due to the friction. So power loss due to the friction is 3.20 horsepower. So in the beginning we had 10 horsepower, but we have a loss of 3.20 horsepower. Then it means the power that's transferred to the water is 6.8 horsepower. So how can you define the efficiency of the pump here? The efficiency is like 68%, right? Yeah. Because 32% is lost. We cannot use it. So the pump efficiency here is 68%. This is the end of this chapter, so we can. This is the end of this chapter, so we can start the next chapter now. I will not finish the next chapter completely because it will not be included in the final exam, but because it's the introduction to heat transfer, I want to have some knowledge of heat transfer, even though it's not included in the exam. Heat transfer is different from thermodynamics. In what sense? Do you know anything about it? They're both related to energy, but thermodynamics deals with something, whereas heat transfer deals with something else. Thermodynamics deals with the energy. So when we say energy, we are talking about joules, calories, so forth. On the other hand, heat transfer deals with the rate of energy. What's the rate of energy? By what rate we mean unit time of energy. So joules per second, calories per hour, so forth. So when we talk about heat transfer, we know that we are dealing with rates of energy or energy per unit time. There are three modes of heat transfer. One of them is conduction, the other is convection, and the third one is radiation. The first and most basic one, conduction, is because of the atomic or molecular activity in the fluids or other substances, solids as well. But whatever the mode of heat transfer, there has to be a temperature difference. Temperature difference is the driving potential of heat transfer. Without the temperature difference, there won't be any heat transfer. It's like without voltage difference, there won't be current. Without pressure difference, there won't be flow. Without concentration difference, there won't be any mass transfer. And similarly, without temperature difference, there won't be a heat transfer. So the first thing to have is a temperature gradient or temperature difference. Temperature gradient is just temperature difference per unit length. It's like the derivative of the temperature with respect to distance. But it's also similar to saying temperature difference as well. So the conduction requires a temperature gradient first, the change of temperature with distance, and it occurs due to the atomic and molecular activity of the substances. What kind of atomic and molecular activities can the substance have? There can be rotational motion of the molecules or atoms, also vibrational motions. So translational, rotational, and vibrational motions of the molecules and the atoms create this transfer of the energy by conduction. So as they rotate or vibrate, they transfer this energy to the adjacent molecule, then it goes on like that. In the case of solids, it's because of the lattice vibration of the solid construction. Otherwise, if it's gas or liquid, it's because of the either diffusion of the energy between the atoms and molecules or bulk motion of the fluid. And in this case, it's actually called convection, but in any case, part of the convection is conduction. So let's give an example of conduction. So suppose that you have a Turkish tea like this. So after a while, the tip of the spoon will get hot. In the beginning, while it was cold, when you dip it into this glass of tea, it will get hot for after a while. This is because of the transfer of the energy through the spoon. So first, the stem of the spoon becomes hot, then this energy or this high temperature in the spoon stem is transferred in the direction of the spoon tip, and of course it's not the same temperature at the base of the spoon. Why it's not at the same temperature at the base of the spoon? So suppose that this is the spoon, right? It's inside the hot water or tea. This side is colder than that side. It's not at the same temperature as the bottom of it. Why? Because it loses heat from the sides. So by the time it comes to the tip of the spoon, it's colder, right? It's not as the same temperature as the bottom. And this motion of the heat inside the spoon is called conduction. And there has to be a temperature difference for the conduction to occur. So this tip must be colder than the bottom so that conduction can take place. So there has to be a temperature gradient. As an example, this is a wall. So this is like the wall of the house. Inside the house can be 25 Celsius, let's say. Outside the wall can be, I don't know, 5 Celsius. So because of this temperature difference, And because of the physical properties of the wall, there will be a flow of heat transfer in the mode of conduction, and it's because of this temperature difference or temperature gradient. As you can see here, the temperature gradient is T1 minus T2 divided by thickness. So what can you say about the amount of heat transfer in terms of the temperature differences and the thicknesses? What happens to the amount of heat transfer if the wall is thicker? It decreases because when you write the gradient, it's at the denominator. If it's bigger, the heat transfer becomes less. Increase in delta T increases the heat flow. So we say that the heat flow is actually proportional to the temperature gradient, meaning that temperature difference increases the heat transfer, the thickness of the wall decreases the heat transfer. So in order to make this an equality, instead of having this proportionality constant, we use a proportionality constant which is called K. So K is thermal conductivity. It's just the proportional constant here. So instead of having a proportionality sign here, I just put an equation here as K times delta T over delta X. And actually there will be area also, because if the area is greater, then heat transfer will be greater. So if you write the conduction equation, which is either K times A delta T over delta X, which gives you watts, or you can also use Q double prime, which is Q over A. So it's the conduction heat transfer per unit area, and it's called heat flux. So heat flux means heat transfer per unit area. So when you use the heat flux, you don't have an area. And why do you think we have a minus sign here? It's minus K dt over dx, because dt over dx is just the derivative of temperature. So what is the difference between delta T over dx and dt over dx? Mathematically, what difference do they have? Dt over dx is actually dt over dx when dx go to 0, right? Mathematically, the definition of derivative, when delta x goes to 0, delta y over delta x becomes the derivative, mathematically. But why then you also have a minus sign here? What is the meaning of this minus sign here? What is dt dx? It's the derivative. What is the mathematical meaning of derivative? The slope, right? Yes. So what kind of slope do you have here? This one is positive slope, and that one negative slope. So in order to get a positive value, you have a negative sign here. So because heat flow in this side must be positive, so to make it positive, you put a sign, minus sign here, because the derivative is minus, negative. The slope is negative. A very simple example. There is a wall of 15 centimeters, a regular wall. It looks like it's an oven wall because inside the oven is 1400 Kelvin, outside the oven is 1150 Kelvin, and the conductivity, the thermal conductivity of the wall is 1.7. As the thermal conductivity is higher, the heat transfer will be higher too, because Q is Ka dt over dx. As you can see, K also increases the heat transfer. For instance, metals like copper, aluminum, they have high Ks, whereas plastic, wood have low Ks. So this wall has a K of 1.7, which is not so high. So we just want to calculate the heat loss from this wall. You can also do this for your house. You can assume that the wall is 20 Celsius, outside is 10 Celsius, the thickness is this. From the wall material, you can find out the K. Then you can calculate the heat loss from this wall. And you have a total area of the heat walls. Maybe you have some heat loss from ceiling, from floor. And at the end, you can have an idea how much heat loss you're having from your house. So by using this conduction equation, by the way, it's called actually Fourier's equation. K is given. First, we are going to calculate Q double prime, which is the heat flux. It's the heat and conduction heat transfer per unit area. So K times delta T divided by L, which is this one, will give you 2,833 watts per square meter of heat. And because you have an area of 0.5 times 1.2 meters, meaning that it's 0.6 square meter, then the heat loss is 1,700 watts. Normally, you have a small boiler at your house for radiators, like they're about 20,000 kilocalories per hour. This is enough for, they're about 20,000 kilocalories per hour. This is enough for a 100 or 150 square meter house. But most of the time, you use only 1/3 of this because it doesn't operate permanently, right? It stops, it operates again. So it's like, let's say 7,000 kilocalories per hour permanent, and it's about 5,000 watts. So if the boiler is operated 5,000 watts, at 5,000 watts, it keeps the temperature constant inside the house. What does it mean physically? If the temperature here is constant, what is actually happening? What is the radiator is doing there? It should provide the energy that's lost, right? Yes. If they're equal to each other, the temperature inside is equal, is constant. So to keep the temperature inside constant, the energy that the radiator gives must be equal to energy loss. So this 500 watts is actually instantaneous energy loss from your house, and this is actually the calculation of the losses from windows, walls, ceiling, floors, and everything. So before starting convection, we'll have a 10-minute break, then we'll be back at 2 o'clock, sorry. The second mode of heat transfer is convection. For the convection to take place, there has to be one fluid. So it's actually the interaction between a fluid and a solid surface. And of course, as in all kinds of heat transfer modes, there has to be temperature difference between the solid and fluid. This is how the radiator in the house is heating the room, because of the surface temperature of the radiator is higher than the air temperature. So convection heat transfer occurs on the surface of the radiator. Actually, it's the combination of two kinds of heat transfer, superposition of both diffusion, which is conduction, plus advection, which is the fluid motion. So when we talk about convection, it's not only because the fluid motion, but also the diffusion, which is the molecular level heat transfer or conduction, also takes place. Suppose that there is a flow over this plate. So we have a moving fluid at a temperature of T infinity, and the plate may be at a higher temperature than the surrounding. So it means that the heat will flow from the hot plate into the surrounding air or fluid that's flowing over it. So this is a typical convection case. There is motion, fluid motion, there is temperature difference, and also right at the surface of the plate there is a little bit conduction too. Remember that we talked about a physical phenomenon called boundary layer. Boundary layer is the fluid thickness in which the velocity changes from zero on the surface of the plate, because molecules stick there. There is zero velocity there. So this is called no slip condition. There is no velocity here. But away from the plate, the velocity increases up to a point where the uniform flow takes place. So inside the boundary layer, velocity varies from zero to maximum velocity at the outside of boundary layer. And the reason why this occurs is because of the internal friction of the fluid, which is determined by the viscosity. So viscosity is responsible for the construction of this boundary layer. So inside the boundary layer, we have frictional effects. So this is the region where friction inside the flow takes place, but outside the boundary layer is a no friction area. So this is also called rotational because of the friction. Remember previous weeks. Outside is called irrotational. Similarly, this is called boundary layer, sometimes hydrodynamic boundary layer, sometimes velocity boundary layer. There is also thermal boundary layer, and similarly, inside the thermal boundary layer, the temperature varies from the plate temperature to the uniform temperature, which is very far away from the plate. The factor that is responsible for the thermal boundary layer is thermal diffusivity. While in velocity boundary layer, the responsible factor is viscosity. In thermal boundary layer, the responsible factor is thermal diffusivity. Thermal diffusivity is alpha, which is K over rho C. K is the thermal conductivity of the fluid, rho is the density of the fluid, and C is the specific heat of the fluid. So the higher the thermal conductivity, thermal diffusivity, the higher the rate of the diffusion of the heat inside the boundary layer. So there are similar concepts, but of course, one of them, velocity boundary layer, is related to viscosity, while the thermal boundary layer is related to thermal diffusivity. We used the Fourier equation in conduction, which was Q K A dt over dx. On the other hand, in convection, we use Newton's cooling law, or law of cooling, which is H times A delta T. H is called convection coefficient, and it depends on fluid and the surfaces and the flow itself. For instance, in higher flows, we have higher convection coefficients. Area is the surface area, the plate area. Delta T is the temperature difference between the surface and the fluid temperature. Depending on the flow, we may have very different H values. For instance, in gases, they may be as small as 2 to 25. In liquids, they can be 50 to 100. Two kinds of convection, free convection and forced convection. Let me explain the forced convection first. If we are using an equipment such as a pump or fan to move the fluid, it's called forced convection. But if the convection, the liquid motion, fluid motion takes place by itself, it's called free convection. How do you think it can take place by itself? For instance, I can say that there is an air motion around this radiator, and it takes by itself. How come? What is the reason of this phenomenon? What happens on a hot surface? It's a hot surface. So nearby the hot surface, the air is warmed up. What happens when some substance is warmed up? When its temperature is increased? What happens to a gas or to a liquid when its temperature is increased?
The energy is getting higher.
Not energy, but think about the physical.
It would turn into a vapor?
No, not that much energy, not that much increase. It will expand, right?
Yes.
Expansion means the volume will increase. What happens when the volume of a M mass is increased? Think about the density.
The density will be decreased.
Yeah, when it expands, the density will be less. So what happens if density is less than the surrounding fluid's density? Think about the Archimedes law. According to Archimedes law, an object will be floating if the overall density of the substance or body is less than the fluid density. In this case, the fluid will apply a buoyancy force, right? The buoyancy force, if the submerged volume is V, the buoyancy force is gamma times V. Gamma is the fluid specific weight. So similarly, if the air adjacent to radiator becomes hot and becomes less dense, it means colder air around will apply a buoyancy on it, right? So this buoyancy will cause this air to move up. So this motion of air will cause the convective flows. So this is how it's heating the whole room. It's very small, it's very far away from us, but yet we know that there's a very slow air motion inside this room because of the convection. The convection, here the convection coefficient is about 5, 6, not that much, but it may be very high for the case of forced convection. So if you use a pump or fan, for instance, if you install a pump fan nearby it, it means that it will move more air, increasing the H. So when you increase the H, you can increase also the convection heat transfer. So normally, this size of a radiator can provide you something like 500 watts or 600 watts. But if you use this fan, you can have a heating capacity of maybe 1 kilowatts because you increase the H. The third mode of heat transfer is radiation. In the radiation, it's not necessary to have a medium. So what do we mean by this? In conduction, there has to be a medium because it's the molecules or atoms that causes the conduction. In convection, we also need medium, actually two media. One medium is solid, the other medium is fluid. But in radiation, it's not necessary to have a medium. Actually, if there is a medium, the amount of radiation becomes less. So it's maximum in vacuum or in space. So this is how the energy of the sun arrives at the surface of the earth. So it's because of the electromagnetic waves or photons. It's a theory because one theory says it's electromagnetic waves. The other theory says it's photons. But at the end, they both explain the phenomenon. And it's created from the changes of electronic configuration in atoms. When the electronic configuration in an atom changes, it releases a photon. And what is the energy of this photon? H times nu. H is Planck coefficient. Nu is the frequency of the photon. So if an electron changes orbit from 1 to 2, so this change of the orbit will cause a photon to be released. And this is how the solar energy leaves the surface of the sun and arrives at the surface of the earth. So how long do you think it takes the photons that leave the surface of the sun to arrive at the surface of the earth? How many seconds, minutes, days? Yep, 8.3 minutes. It takes 8.3 minutes for the sun energy, sun electromagnetic energy to arrive at the surface of the earth. Actually, only a small part of it is visible light. So there is all kind of spectrum coming from the sun, but we only see some portion of it. So this some portion of it has a wavelength of between 0.4 to 0.7 micrometers. So the wavelength of the electromagnetic waves between 0.4 to 0.7 micrometer is called visible light, and less than 0.4, for instance 0.3 is UV, greater than 0.7, for instance 1 micrometer and so forth is called infrared. And actually, the thermal radiation is between 0.1 to 3 micrometers. So inside the thermal radiation frequency band, only this part is the visible light, and other part of the band cannot be seen by eye, by at least human eye. Maybe some animals can see them, can see infrared, we don't know. But this is what we call thermal radiation band, because this is the part of the electromagnetic radiation that causes the radiation heat transfer. We use the concept of emissive power. Emissive power is calculated from sigma times T to the fourth. Sigma is called Stefan Boltzmann coefficient. It's just a coefficient, very small, 5.67 times 10 to the minus 8. T is the temperature of the surface in Kelvin. So if a surface has a Kelvin temperature, take the fourth power of it times the Stefan Boltzmann constant, will give you the emissive power of the surface in watts per square meter. For instance, the surface of the sun is about 6,000 kelvins. So 6,000 kelvins to the fourth power times the Stefan Boltzmann constant will give you the emissive power of the sun. But if you compare the sun and the world, Earth is very small with respect to sun. As volume, there can be 1.3 million Earths inside the sun. So Earth is this big, the sun is this big, Earth is very small. So because of the size of the two objects and because of the distances between them, not all the energy arrives on the Earth, of course. This is the total emissive power from the sun surface. So if you calculate the portion of the energy leaving the sun, arriving the Earth, you get the actual solar energy received by the Earth. Do you have any idea how much is that in watts per square meter? The solar energy. So this is sun. And this is Earth. The amount of emissive power from sun is so many watts per square meter. But the portion that arrives on it is only 1,300 watts per square meter. And this is outside the atmosphere. When it enters the atmosphere, this atmosphere, let's say, it will be attenuated because of the absorption inside the atmospheric gases or dust or whatever, or humidity. So the portion that arrives on the surface of the Earth is about 1,000 watts per square meter. So this is the maximum solar flux that is used in the design of the collectors, design of the solar panels. So you start with this value. What is the efficiency of a solar panel? It's about 20%, right? So it means that a solar power panel of 1 square meter provides 200 watts. So it starts with a very large value. Outside the atmosphere is 1,300. On the surface, its maximum 1000. And because of the conversion efficiency of solar panels, which is recently 20%, it used to be much less than this. Maybe in the future it will be greater than that, but for the time being, you can get 200 watts per square meter of solar panel. On the other hand, if you are using it as a parabolic heater, right? You can have a parabolic heater where the solar light can be concentrated on a pipe. You can concentrate the solar light on a pipe. Then in this case, of course, you can utilize most of it because the conversion efficiency here is much greater than there. So the calculation of radiation is always related to a surface temperature. What it means is actually in the deep space, the temperature is how much? Where there is no material, there is no substance, no molecules.
Almost zero.
Absolutely zero. Because the reason why there is the sensation of temperature is because of the energy of the molecules. So the temperature we feel here is because of the molecules that are having kinetic energy. As they hit our faces, this sensation is actually because of their energies. So the temperature is actually another expression of the amount of energy content in the fluid, in the air. So when the temperature is higher, it means that the molecules have higher kinetic energies. Normally, the air molecules have a velocity, because when we say kinetic energy, we are talking about 1/2 mv squared, right? So what do you think the magnitude of the velocity under normal conditions? In this room, it's 20 Celsius. So what do you think the velocity of the air molecules, let's say nitrogen molecules or oxygen molecules? How much do you think they have energy? They have temperature, velocity? Their velocity is almost 500 meters per second. They really move fast. But they don't start here and go to the door because they have a mean free path. Mean free path is the length at which they collide before they move ahead. So the normal distance between two molecules before they collide is about 0.5 micrometers. They're very small. They have very high velocities, but they don't go for kilometers. They just collide with another one before they move something like 0.5 micrometers. When the temperature is higher, you can understand that this is higher too. If you cool the air so much that the temperature will be zero, what happens to the molecules? They just stop. So a molecule that has zero velocity means that it has zero energy, or in other words, in that medium, the temperature is absolute zero.
And what about the electrons inside the molecules? Are they stopped too?
I don't think so. They must move because the charge of the electrons still there.
Yeah.
They cannot stop. They should be moving around the nucleus. It's only the motion of the molecules. So electrons must be rotating around the nucleus. Because this is why they have an electric charge. So with this motion, they have this electric charge. Of course, this is all theory, right? Nobody has seen them yet. So, a surface will have an emissive power of sigma times T to the fourth power, and also a surface can absorb radiation, solar thermal radiation by an amount of alpha times G. G is the irradiation amount. Irradiation is the amount of watts per square meter coming to a surface, and only an amount of alpha is absorbed by it. So alpha is absorbed, but some other portion of the incoming radiation, which is called irradiation, is either transmitted. For instance, if it's glass, we have sunlight out there, right? Sunlight passes through the glass. Some of it will be transmitted, some of it will be absorbed because it gets warm, and some of it will be reflected. So there are three things: absorption in the material, transmission passing through the transparent materials, and reflection from the surface. So if the alpha amount is absorbed by the surface, then the remaining part will be either transmitted or reflected. This is why we have very high temperatures on the asphalts during the summertime, right? Because it's black. Black absorbs the maximum radiation. And if you measure the temperature of asphalt, it could be close to 100 degrees, whereas the temperature outside is only 30 degrees. It has nothing to do with the air temperature. It's because of the radiation absorbed by this black surface. So we said that radiation energy can be absorbed due to incoming irradiation, and this same surface can also emit radiation because of its surface temperature. So while it can absorb some energy from some source, it can also emit radiation. So the net energy for this surface will be the emitted radiation. Here in the emitted radiation, you use epsilon times EB. Epsilon is the emissivity of the surface. Emissivity depends on the surface characteristics. For instance, if it's a black surface, emissivity becomes 1, meaning that it emits the maximum amount of radiation. If emissivity is very small, like close to 0, if it's a shiny surface, then emissivity becomes almost 0. I don't know if you have seen the engine department of a bus. Inside the engine department of a bus, they use aluminum foil. For instance, this is the bus. This is the engine department of the bus. Here they have the engine here. They cover this part with aluminum foil. Why do you think so? Because aluminum foil is very shiny and emissivity is almost 0, meaning that this surface will not receive any radiation from this hot surface of the engine, because the engine surface can be around 80 or 90 Celsius. And because it reflects all the radiation coming onto it, it will not transmit it into the bus, right? It's like an insulation. So this is why firemen also wear aluminum clothing in petroleum fires, for instance, or in big fires, they wear aluminum clothing because of this. So the net radiation coming and leaving a surface is epsilon EB, which is the emission, minus alpha G, which is the absorption. So some energy is absorbed while some energy leaves the surface. For many surfaces, alpha is equal to epsilon, so you can write the net energy, radiation energy, to and from a surface. So you can write the net energy, radiation energy, to and from a surface to be epsilon times sigma times T surface to the fourth power minus T surrounding to the fourth power. Why do you think the surface of the grass may be covered with ice in the cold mornings of some winter days? During some winter days, you wake up and see something like snow on the snow on the grass. Crow, yeah. Why do you think so? It's because of the thermal radiation from the ground, from the grass, to the deep sky. Because it occurs when there is no cloud, when the air is very clear, meaning that this grass is seeing a temperature in the deep sky which is very low, not absolute zero, but I don't know if you notice the temperature when you fly at 10,000 meters. Do you have any idea what is the temperature? They have indicated.
Might be super cold, I suppose.
Yeah, it's around minus 70 degrees. So there is a loss, heat loss from, let's say, 0 degrees or 1 degrees on the grass to a temperature which is at minus 70 degrees. You need to convert them to Kelvin anyway. So the amount of heat loss from the grass to the space, to the atmosphere during the night is this much. And this is why this heat loss will cause the surface temperature to go down. If it goes down below zero, it will freeze. The humidity on the surface will freeze. Normally we have humidity here in the air. If the temperature goes below the dew point, this humidity will condense, it will rain, right? If you drop the temperature even lower, it will freeze. So this is why you have a snow-like appearance on the grass surface during a cold, clear night of a winter day. And it's most of the time the case that there can be convection plus radiation occurring together. For instance, during the occurrence of this snow-like thing on the grass, it can be also helped by convection, which can be a wind blowing on it, removing some energy by convection. So most of the time we may have convection and conduction, radiation together. For instance, this radiator is not convecting only, but it's also radiating. That's why it's called a radiator. Actually, half of the energy it's providing to this room is convection. The other part is convection because of the convective heat transfer coefficient. You can say that 400 watts from convection, other 400 watts is from radiation. So most of the time you have a situation where the total amount of energy leaving the surface is partly because of the convection and radiation. An example here, a steam pipe of 200 Celsius is not insulated, so it's there is no insulation on it, so the surface temperature is 200 and surface emissivity is given as 0.8. It's not 1, it would be black. It would be 1 if it was black. So black surface has an emissivity of 1. A very shiny surface has a very small emissivity, but this one has an emissivity of 0.8. For instance, we have emissivities of 0.7, 0.8. The walls are the same. But this shiny surface may have a very small emissivity. In any case, it's given to you. So the surrounding temperature is 25 Celsius and the heat transfer coefficient is given there, 15. So it looks like there is a motion in the air because in a standstill air, the heat transfer coefficient is about 5, 6, but in a moving air, it can be higher. Here it's higher. Also, there is a wall nearby which is also at 25 Celsius. Why all these are given to you? Because we would like to calculate radiation plus convection from the surface of the steam pipe. So incoming, the emitted energy from the surface of the pipe is emissive power, epsilon times sigma times T surface to the fourth power. This is the emissive power of the surface of the pipe. And irradiation from the surrounding is sigma times T surrounding to the fourth power, so that the net amount is the difference between them, because there is an incoming radiation, there is a leaving emission, so the net amount is the difference between them. On the other hand, there is also a convection amount. So this first part is related to convective part, the second part is related to radiative part. Here the area is the side area of the pipe, which is pi times d times L. It's a cylinder, but you are talking about the side area. So H times area times delta T is the convection. Epsilon times area times sigma times the differences of the fourth power of Kelvin temperatures is the radiation. So it's the net heat transfer from the pipe is calculated to be almost 1 kilowatts per meter of the pipe. It's a very large value. If it's a 100 meters pipe, then it would mean 100 kilowatts of heat loss. So what can you do about this? It's an uninsulated pipe, so it means that you need to put insulation on it, right? So what happens when you put insulation on it? It's a resistance. So when you put a resistance in an electrical circuit, when you add resistance, what do you change? When the resistance is higher, what becomes lower?
The current.
Current becomes. So here, if you put insulation on the pipe, which is a thermal resistance, you reduce the heat flow. So instead of 1 kilowatt, it becomes 200 watts or something. I don't know. It depends on the amount of insulation. This is why we put on heavy suit during the winter. Why? Because it's a thermal insulation, so that you don't lose heat. The insulation of the heat is actually the clothing during the winter is actually the thermal resistance we put on. Because the body temperature is 37, outside is 10. So the more the resistance, the less the heat transfer. Remember that in thermodynamics, we use the concept of conservation of energy. According to conservation of energy, the sum of the total energy, whether it's in terms of work or heat, will be causing a change of the system's energy. So in thermodynamics, we wrote it as the net Q in and out of the system minus W in and out of the system is the change of the system energy. Or you can write it, this is rate basis per unit time. You can write it as this also. So this is in joules, this is in watts, but they are similar. It's also possible that the energy can be generated within a system. So can you tell me an example about energy generation within a system? If this is a resistor, if current is passing through it, energy is generated at a rate of I squared R, right? So this is an energy generation. What else? You have uranium rods inside a nuclear reactor, right? There are many uranium rods in a nuclear reactor, and as they release neutrons, they generate energy. So we need to put another term here to account for the energy generation. So this energy generation can also be added into this equation. But for the time being, we have energy in, energy out, energy generation, and some part of it can be stored. So as this resistor becomes hot due to the current passing through it, it does not get hot indefinitely, right?
Yes.
So after a while, you see it red or something, the temperature is something, but it stops there. So it means that it becomes steady state. Why do you think it becomes steady state? Because the energy input and energy output as heat loss is the same. So after a while, the temperature of it becomes constant. But up to this point, what happens? Its internal energy keeps increasing, right? When it's at a steady state, this energy change, the internal energy change becomes zero. So up to this point, the energy of the resistor increases. It stores energy up to a point, but after some point, it doesn't change anymore, which means it has arrived at a steady state. Generation of energy can be given as per unit volume, such as in the case of resistors. An example here, a long conducting rod of diameter D and electrical resistance unit per unit length R prime E. R prime E actually the unit resistance. So it's given as resistance per unit meter. So resistance per unit meter is given. The equilibrium condition is disturbed when an electrical current I is passed through the rod. Develop an equation that could be used to compute the variation of the rod temperature with time during passage of the current. We're not going to solve this, but we will make a mathematical model that represents this physical situation. What is the physical situation? There is a conducting rod, current is passing through it, while there is convective heat loss around. So we're going to develop a mathematical model for this, but we're not going to solve it because it's complicated. So what is E out? E out is the energy loss due to the convection plus energy loss due to the radiation. What is the storage of the energy, du dt? It's because U is MC delta T, du dt is rho Cv dt dt. So we can write the net energy in and out of the system, because E in plus E generated minus E out should be equal to E stored. Then if we put everything in this equation, this is the generated heat. This is E in, or E generated, sorry. There is no E in, there is only E generated, minus loss by the convection, minus loss by the radiation, and everything must be equal to change within the system energy. So you have a differential equation that says the temperature change within this resistor is calculated from this equation. You cannot solve it by hand because it's a differential equation. What happens at the steady state? At the steady state, the temperature does not change anymore. So the left-hand side will be 0. When it's 0, you can solve it by iteration, right? Because here T is the unknown one. So you can solve it more easily than the upper one. But even then, it's not so easy to find it by hand. Okay, let's have another break. Then I will not finish this chapter. A few pages later, I will start reviewing. So we will start reviewing from chapter 5 very fast, then talk about the exam. Okay, see you at 3 o'clock. Then not finish this chapter, but we will do the review part. So surface energy balance, remember that if it's a mass of substance, then you have to consider not only the heat generation, but also the heat storage. On the other hand, if you're talking about a small boundary, a very thin boundary, so thin that its mass is 0, then in this case, the energy cannot be stored in this very small, very thin boundary, but the energy balance should still be there, meaning that E in must be equal to E out. All others are 0. We are only left with the E in and E out. This is called a surface balance. What is a surface balance? For instance, we have this wall. Inside the wall, we have conduction. And right outside the surface, we may have radiation, and also we may have convection. So according to the energy balance, the conduction, must be equal to convection plus radiation. So it means that whatever comes in any mode of energy transfer must be equal to the energy that leaves the surface. So this is different from other analysis, because in the other analysis we also considered generated energy plus stored energy, which are 0 here. Again, we are working with a wall of 15 centimeters. The wall material is 1.2 watts per meter per Kelvin in conductive coefficient. The surface of the wall, outside surface, is 100 Celsius. The emissivity is 0.8. Now, we will say that because the wall is a very thin surface, the conduction energy must be equal to the sum of the convection and radiation. So we will set equal the conduction inside the wall to convection plus radiation. So this is the equation. energy balance, E in minus E in is equal to E out, meaning that on the surface, conduction and convection must be equal. So incoming ones are plus, exiting ones are minus, which means conduction minus convection minus radiation is 0. So conduction is K times delta T over L. Convection is Newton's cooling law. Radiation is Stefan Boltzmann theory, law, Stefan Boltzmann law. So if you put everything together, you have an equation, and by solving this equation, you get a total heat leaving the surface to be 2020 watts per square meter. So from here, you can also calculate the surface temperature, inner surface temperature here, because this amount is equal to, this total amount is equal to conduction according to this. So because this is equal to T1 minus T2 divided by L, you can calculate the inner surface of the wall, and inner surface of the wall is found to be 352. Another example, a plate is cured, coating is applied on a plate, so you can see that there is a coating on this plate, and it's cured by a hot infrared lamp. So this is an infrared lamp which gives an irradiation of 2000 watts per square meter. You may have seen infrared lamps, for instance, even in the restaurants, they use infrared lamps. Did you see them? To keep the meat hot. So in some restaurants, you may see meats served in the open buffet. Inside the open buffet, you may have infrared lamps to keep the meat hot. So here, similarly, this infrared lamp is curing the coating or making it dry, in other words. So the irradiation amount is 2000 watts per square meter, but only 80% of it is absorbed by the surface, so 20% is reflected by the surface. So 2000, 80% is 1600 is absorbed, whereas 400 is reflected from the surface. And the surface emissivity is different from the absorption. It's given as 0.50. Temperatures are given, like surrounding temperature, and so it's asking what would be the temperature of the coated plate. So we are interested in finding the temperature of the coated plate, but it also says that the bottom of the plate is insulated. What does it mean to have an insulation? If you have a perfect insulation, a perfect insulation means that perfect insulation, think about it electrically. What do you have resistance in a perfect insulation? Infinite, right? So that the current is 0. This is why you wear protective gloves when you work with electricity, because their resistance is infinite. So even though you touch a live section of the circuit, 200 volts, 400 volts, whatever, you don't get an electric shock because there is no current passing through your body because of the high resistance of this glove. Or your shoes might be suitable for working with electricity so that it don't earth you. Even if you touch a voltage carrying conductor, you don't get an electric shock because of the current not going to the earth. Or what else? Any insulation on a cable keeps the electric current from leaking outside because its resistance is also infinite. So this is like an infinite thermal resistance, which means Q to the bottom plate is 0. It's not losing any heat from the bottom. So in this case, there is nothing lost by the bottom. We have a surface balance of the energy. What is the surface balance of the energy? We have incoming radiation, we have emissive radiation, we have convection, and they should be all in equilibrium. So if you put it in mathematical way, this is the E in, the irradiation coming from the infrared lamp. This is the convection lost by the surface of the plate, which gets hot because of this irradiation. Then emissive power from this plate, because it will also emit radiant energy. You have irradiation, convection, emission from the surface. So the surface temperature is found to be 104. Very similar to this, you can also calculate the surface temperature of an asphalt, right? So for asphalt, you may assume the irradiation as 1000 from the sun. You can take the alpha almost 1 because it's a black surface, and you can assume some surrounding temperature like 30 degrees during summer. So by inserting the numbers, you will get a surface temperature for the asphalt, I don't know, 95 Celsius or something like this. So this is very similar to the problem of asphalt, but not exactly actually, because asphalt is also losing energy to the bottom of the asphalt, right? This one is insulated from the bottom, but asphalt not only losing energy as convection and radiation, but also losing energy as conduction to the bottom of it. But you may assume something. In any case, you can obtain a figure that gives you some information regarding the temperature of the surface temperature of the asphalt. It would be an estimate, but in any case, it gives you some idea. Thermos bottles or thermostatic bottles are used to keep fluids at the same temperature, right? If you put hot coffee inside the thermos bottle, it will stay hot there. Or if you put cold water in there, it would keep its temperature as it is. So what is the principle of a thermos bottle? How come it can keep the temperature constant for several hours? For instance, you can keep coffee hot for, I don't know, 5 hours, 6 hours, depending on the quality of the thermos bottle. So why do you think a thermos bottle can keep the coffee hot for several hours? First of all, there are two containers, one outside container, one inside container. An inside container is usually glass. And if you have seen a broken thermos, you will see the outside surface of this glass to be very shiny, right? Because it is intended to prevent the radiation between this surface and outer surface. Also, there is either vacuum. Vacuum means that there is no conduction in the in this gap, or air. Air is not a good conductor, so either air or vacuum. There is another, so this one is another thermal resistance. So it starts with Q1 inside the coffee. In the tank, in the plastic tank, here in the plastic tank, it says plastic, but it can be glass also. We have Q2. We may have some radiation, some convection, and it passes through the outer cover. Then from the outer cover, there can be another radiation and another convection. As you can see, because of this shiny surface, because of very low emissivity in the on the inside container, you have a resistance due against radiation. Then in the gap, you have a resistance in radiation, also in convection. Then in here, you have a resistance due to the conduction. Then outside, you may have a resistance due to the convection. So if you consider the overall resistance of this, it will be not infinite, but will be very high. So if you consider the whole network of the resistances, it will be very high, meaning that even if the temperature inside is 90 Celsius, the coffee temperature, and outside is 25 Celsius, delta T over R will be almost zero, which is the heat transfer from the coffee to the surrounding. So you can read the summary of this. Free convection from the coffee to flask, conduction through the flask, free convection from flask to airspace, free convection from airspace to cover, net radiation exchange between the outer space of flask and inner surface of the cover, conduction through the cover, free convection from the cover to the room air, net radiation exchange between the outer surface of the cover and surroundings. So these are all thermal resistances. If you consider the complete network of the thermal resistances, this is why we have a very low heat loss from inside to outside, and this keeps the coffee inside the thermos to be very low. Suppose that in the beginning we had 90 Celsius of coffee. In 5 hours, the temperature of the coffee dropped 70 Celsius. Can you calculate the heat loss? And let's say the coffee inside is 0.5 kilograms and the CP of the coffee, which is water, 4.20 kilojoules per kilogram per Kelvin. So how can you calculate this? What is the change of the internal energy of the coffee? Because the conservation of energy says that E in minus E out is equal to du dt, right? There is no E in, but there is E out, which is the heat loss. So heat loss is equal to du dt. And how can you write the du dt? MC dt over dt. You know the mass of the coffee, 0.5 kilogram. The C is 4,200 times dt over dt is 20 Celsius divided by, it's in 5 hours, so 5 hours is almost 18,000 seconds. So 18,000 seconds. So you get some watts here, which is very small. So this has to be very small, because otherwise it would be cold in a short time. And this watts is also equal to, in average, is also equal to T average minus T surroundings divided by sorry, this is not here. So delta T over Tr. You take an average temperature. The average temperature here is 80 Celsius. So by using 80 Celsius average temperature, you can also calculate the total resistance, right? And total resistance is the resistance that you can calculate from the network of the resistances. So this is where I will stop. Now let's do a quick review of the previous chapters. The first chapter is chapter 5, which is the vapor systems in power generation and vapor systems in refrigeration. Water is used in vapor power systems. In the vapor power systems, we have always 4 units, 4 members, 1 boiler, then 1 turbine, then 1 condenser, then 1 pump. So this is always what we have in a vapor power generation system. And this one also has the same thing. In the boiler, we add heat by combusting some fuel. It could be nuclear power plant, so it could be the reactor of the nuclear power plant. But in any case, as we add heat here, water becomes vapor, right? It vaporizes. This vapor rotates the turbine, and the turbine generates electricity, or it can drive the propeller shaft of a ship. Then it has to be condensated, because otherwise, if you don't make it liquid, you cannot pump it back into the boiler. So here we have to lose some energy. As condensation takes place, we have to make some cooling, meaning that we have to lose some energy. In the turbine, we obtain turbine work, but in the pump, we need to put some pump work, but pump work is usually only 1% of the turbine work. So it's a small amount of work, but we usually calculate it also. All the interactions are done by the enthalpy differences. So this is a typical simple TS diagram, let's say. S is the entropy. From 4 to 1, sorry, 3 to 4, liquid is compressed. Then when it enters into the boiler, first its temperature is increased, then in constant temperature it changes phase, then it becomes superheated, 0.1. Then in the turbine, as it expands to low pressure, it produces work. Then in the condenser, as the heat is rejected, heat is added here, heat is rejected there, then it becomes liquid. So in all the interactions, we always use the difference in the enthalpy. So in order to find the pump work, we do H4 minus H1. In order to find this, we do H4 minus H3. For this one, H1 minus H4. For this, H2 minus H1. And for that, H2 minus H3. So as you can see, all the calculations, whether it's heat addition, heat rejection, pump work or turbine work, is always the change, the difference in the enthalpies. So what is the efficiency of the system? The efficiency of the system is calculated always as some output divided by some input. What is the output here? What is the purpose of this system? Why do we use this power generation system? To obtain power, right? So the output is net power, turbine power minus pump power. What is the input of the system? What do we add to the system? Is the heat in the boiler, right? So always the efficiency is defined as some output divided by some input. Now that this is a system to produce work, the output of the system is the network of the system. Network of the system is turbine work minus pump work, even though the pump work is much smaller than the turbine work, divided by input to the system, which is the heat input into the boiler. Back work ratio is the ratio of the pump work to the turbine work. So this ratio is most of the time in the vicinity of 0.01% of turbine work. It's small, but we can calculate it anyway. Back work ratio is much greater in gas turbines because in gas turbine derives the compressor, and almost 60% or around 50% of the turbine work is used for operating the compressor. So even though it's very small here, there are cases where this back work ratio can be very high. So this is a typical system, ideal Rankine cycle. It's called Rankine cycle. Starts with a liquid in the condenser, then it's pumped to a higher pressure, then its temperature is increased in the boiler, then in the boiler it changes phase from liquid to vapor, then it becomes superheated, then as superheated it gets into the turbine. As it expands in the turbine, it produces work. So here we have Q in, here we have W pump. Then as it leaves the turbine as a mixture of vapor and liquid, we have to convert it to liquid by passing it through the condenser. And in order to do this, we have to lose some energy. Pump work can be calculated from V3 times delta P because liquid is incompressible. So V3 is approximately equal to V4. So we can assume that it's constant so that the pump work is just V3 times delta P. Delta P is the difference between the P boiler minus P condenser. So this is, we have two pressures here, one boiler minus P condenser. So this is, we have two pressures here, one condenser pressure and one boiler pressure. So the product of this will give you the pump work per unit mass of the fluid. So this is a numerical example, but this one does not use superheat, right? It's a saturated pressure, saturated vapor boiler, so it doesn't overheat it. There are many ways to increase the efficiency of a Rankine cycle. Actually, what is done is to increase the area under this curve, because the area under this curve is PDV curve, or it's also TDS curve. So in order to increase this area, which is equal to network, you can use a higher boiler pressure or a lower condenser pressure. There are many ways to increase the efficiency of a Rankine cycle. Also, we assume that both the pump and the turbine is irreversible. Isentropic means reversible plus adiabatic. Reversible means that there is no friction in the pump or the turbine. Adiabatic means that they're not losing heat, they're not exchanging heat with the surrounding. But normally, if they are not isentropic, this expansion can be such that entropy can increase, or this compression can be such that entropy can also increase. So by using this concept, you can define the isentropic turbine efficiency and isentropic pump efficiency. They may be in the vicinity of 80 or 90%, 85%, 75%. So here there is an example to this. So the pump and turbine is not isentropic, so you may be given the efficiencies, isentropic efficiencies for both pump and turbine. So by using this, you can do all the calculations. They are actually the same examples, but with some additions. For instance, they use the same data, but this one says the pump and the turbine is not isentropic, so you can see the effect of the turbine and pump, which are not isentropic. So it's possible to reheat the vapor inside the boiler so that superheat the vapor, so that instead of using a saturated vapor, you can also use superheated vapor. The efficiency of superheated vapor boiler is higher than the efficiency of the saturated vapor. Another addition would be reheat. So what do we do in reheat? Normally, the boiler exit is superheated. It gets into a high pressure turbine. So this is a high pressure turbine. There are two turbines connected on the same shaft. So the exit of the high pressure turbine goes back to the boiler again, and it's reheated. So as it's reheated, it gets into the low pressure turbine. So we have two types of turbine work here. High pressure turbine plus low pressure turbine is the total turbine work. Then the rest is the same. So if you take a look at it on the TS diagram, as you can see, the pump is 6, 5. It gets into the pump as 5. It's compressed isentropically. It gets into the boiler. Temperature is increased. Phase change, superheated. So in the superheat, it gets to the high pressure turbine. In the high pressure turbine, as it expands to this pressure, it produces a work of high pressure. Then it gets into the low pressure turbine. No, it goes back to the boiler to be reheated to some other temperature. So after the reheat, it goes to the second turbine, which is the low pressure turbine, then to the condenser. So by having a reheat, it's possible to increase the efficiency of the Rankine cycle. There is a numerical solution here. You can take a look at it. And it's another modification of it is the inclusion of isentropic efficiencies in the both turbines. So as a modification, we would like to see the effect of isentropic efficiencies in the turbines. And you will see that overall efficiency will be less because the turbines are not isentropic. So there may be other modifications to the system, such as some vapor could be taken out from the first stage into an open water heater. Then it can be combined with the exit of the condenser, but you just can skip this. Don't spend time on this. Also, the numerical example can also be skipped. Now, vapor refrigeration system is another vapor system, but this time we are not producing power, but we are producing refrigeration. So, do you remember the heat engine and refrigerator difference? What was the reason of using a heat engine versus refrigerator? The objective of a heat engine is to produce work, right? The objective of a refrigerator is, what's the objective of your refrigerator at home?
Cool down.
Yeah, to remove heat from a low temperature medium, right? Because inside the refrigerator is colder than the outside. Normally, it's not possible to move heat from a lower temperature to higher temperature because as principle, heat always is transferred from high temperature to low temperature. So normally, if you unplug the refrigerator, what would happen is the temperature inside the kitchen is higher, so heat is going to move from the kitchen into the refrigerator, but you don't want this, right? Normally, you want to keep the refrigerator cold. So how can you keep the refrigerator cold and still remove heat from the lower temperature and transfer it to a higher temperature? By using external energy, right? You use a compressor, so you add energy into the system, which will help remove the heat from low temperature and transfer it to high temperature. So by adding this work, it's possible to remove heat from low temperature and transfer it to high temperature. No, you normally remove heat from the cold temperature inside the refrigerator and it's transferred into the kitchen. So if you hold the back of the refrigerator, you will see that it's warm because heat is transferred to the kitchen there. It's absorbed from the inside, from the food, plus the work from the compressor, and the sum of the two energies is transferred to the outside from the condenser. So you have four elements here also. One element is evaporator, where the heat is removed. This is inside the refrigerator. You have a compressor always, where the energy is input into the fluid. Then you have a condenser where the heat is rejected. Then here it says it's a turbine, but it's not practical. You should use an expansion valve here, where the liquid from the condenser is expanded into a vapor-liquid mixture. This is a Carnot refrigeration cycle. It starts with a mixture of vapor and liquid. As it's compressed to a higher pressure, it becomes saturated vapor. Inside the condenser, as the heat is rejected, it becomes saturated liquid. Then this saturated liquid is expanded through the expansion valve, and when it goes to a lower pressure, it evaporates, and as it evaporates, it absorbs heat from the surrounding. So the principle of refrigeration is the refrigerant, as the refrigerant is evaporated, it absorbs heat from the surrounding. When you push the button of a spray, as it expands, the liquid inside the spray expands as the mixture of vapor and liquid, right? And you feel your finger to be cold. Why? Because as it's evaporated, it absorbs heat from the surrounding, which is the heat absorbed from your finger in that case. Or if you release, I don't know, pressurized air from a tank, you will see that the valve will be cold because of this sudden expansion. As it expands, it will absorb heat from the surrounding. So this is the principle of the refrigeration. So in the refrigerator, we do not use efficiency. Instead, we use coefficient of performance. And coefficient of performance is again some output divided by some input. What is the output of a refrigerator? It's not engine. What's the output of a refrigerator? What do you get out of the refrigeration amount, right? The cooling amount. What's the input of a refrigerator? The compressor work. So definitions are different, but the concept is always the same. By the way, even though the efficiency is always less than 1, the coefficient of performance can be most of the time higher than 1. This is the difference between the efficiency. So the solved examples require that you use the tables. In the vapor systems, you use the water tables, whereas in this refrigeration systems, you may use, for instance, on R134A refrigerant tables as an example. Maybe you may be given ammonia table. Maybe you may be given some other refrigerant table, but they're all the same. They have all pressures, enthalpies, etc. Here, irreversibilities, instead of a turbine, an expansion valve is used. So when we use expansion valve, in the expansion valve, H is constant. So H in and H out in an expansion valve is the same. So enthalpy does not change in an expansion valve. Heat pump systems. What is a heat pump? Normally, in a refrigerator, we have an evaporator, then a condenser, then a compressor, then a condenser, then an expansion valve. So in evaporator, heat is absorbed. We have to provide work here. In the condenser, heat is rejected, and nothing happens in the expansion valve because enthalpy remains the same. So in a refrigerator, we use this side. We keep inside the refrigerator cold. Or in an air conditioner system, during the summer, we use this side, meaning that we keep the room cold. However, in the winter time, we can switch the tasks of condenser and evaporator. So in this winter time, you could use this part, right? Because this part rejects heat. So by just changing the mode of operation in your air conditioner, all of a sudden it becomes a heater because you just replace the roles of inside unit and outside unit. Normally, in summertime, the inside unit is evaporator, which absorbs heat, makes the surrounding cold. And external unit, outside unit, is a condenser, which rejects heat. If you switch the roles, then inside unit becomes a condenser, which rejects heat, becomes a heater, and you don't care about the external unit. It just absorbs heat from the surrounding. But the important thing is it absorbs the free energy available outside. So it comes free. You are using the energy of the surrounding actually. This is why the use of the heat pumps are much more energy efficient than using electric heating. Because in the case of a heat pump, the coefficient of performance is Q heat, which is the output of the system, divided by Wn. So if you compare this, you will find a value such as, let's say 4, which means that you get 4 times heating with respect to electrical energy input as compressor power. Normally, if it was resistance heating, you would get 1 kilowatt heating from 1 kilowatt resistance, electrical resistance. But for the heat pump, you would input 1 kilowatt of compressor power, but you get 4 kilowatt of heating. This is why they are so energy efficient. But of course, the operation of them are dependent upon the external temperature, because if the outside temperature is very low, then they're not efficient anymore. They do not provide necessary heating. But under normal climate conditions such as Istanbul or Izmir, they can be easily used. But you cannot use them in, for instance, Erzurum, because outside temperature is very low, meaning that it's not possible to absorb energy from the outside air temperature. So you see the changing position of the gas flow. So as the position of gas flow changes, inside and outside units of the air conditioners change roles. So while in the cooling position, inside unit was evaporator, outside unit condenser. In the heating position, inside unit becomes condenser, outside unit becomes evaporator. So we don't have time to review the other chapters, but other chapters are more recent than that one. So I suggest that you go over the chapters, try to understand the solutions of the problems. I will provide all the formulas, all the tables, all the charts. So in your summary sheets, you can only maybe writing some examples which you find difficult or complicated, I don't know. So don't waste your summary sheets with tables or anything. Any questions? Okay, I wish you enjoyed the semester. So I see you in the exam at the end of May. I think it was 26th of May. Yeah, 26th of May. So until then, good luck for your examinations. See you. Bye.